Okay, good morning, everybody. So I will just wait till more people join in. So none of the TAs are here yet. Okay, so there is going to be a quiz today. So we will do it in the last 10 minutes, and then after that we will give you another 10 minutes. So I will talk for about 50 minutes, just so that we can cover some important portions. So meanwhile, are there any questions from the class regarding yesterday's class or any general things? So, yeah, okay. Okay, so it's 11:30 and there's a good amount of students already present. So we will begin. So let me share my screen. All right, so yeah, so let me start today's class. So yesterday we were talking about this idea of conditional probability. And maybe let me just choose a conditional probability and conditional expectations. We were talking about this. So then we reviewed some of the concepts that we have already been studying. So things like conditional probability mass function. So for discrete random variables, okay, we saw that what is the meaning of pxy, x given y. So we saw this as basically pxy of x comma y divided by py of y. Okay, so this is first thing we saw. We also saw what is the meaning of conditional PDF. Okay, so this is for continuous. So this is fx given y. I'm sorry, this has to be capital letters. So let me just erase this. So this is f of x given y of xy. So this we saw is this. So this was the second concept that we saw. Thirdly, we saw that expected value of x given y. Okay, this is just like this is a function of a random variable y. Okay, so this is something like, it is something like g of y. Okay, then we also saw that when you put expected value of x given y, sorry, again I put this. So expected value of y equal to y, this is similar to basically g of small y. Okay, so this is like trying to evaluate at a point. This is the general function. Okay, so this analogy is very important. I hope everybody has understood this. Okay, so we saw this. Then fourthly, we saw basically what is the relationship between expected value of x and expected value of x given y. Okay, so if you want to understand this, you can have a mental picture of, so let's say this is your entire omega, and what you are doing is you are dividing the omega into y equal to, let's say 1, y equal to 2, y equal to 3, and y equal to 4. Okay, imagine that like this is the entire class of, I mean the third years. Let's say these are all the third years in IIT Goa. Okay, so and y equal to 1 is, let's say it is computer science, this is math and computing, maybe this is mechanical engineering, and then this is others. I don't know what are the others, maybe electrical or whatever. So these are all the others. So x is, let us say, average age. Okay, so basically if I want to find the average age of all the third years, there are two things I can do. Either I can find the average age in each of these things. So let's say the average age here is 19, 20, 19, 19.5 maybe, right? So how do I find the average age of IIT Goa third years? What I need to do is basically I have to find out, so for every number 19, I have to see how many CS students are there, okay, plus 20 into how many math and computing students are there, then 19.2 into how many mechanical engineering students are there, and then 19.5 into how many others are there. And then I have to divide by the sum of all these students, number of third years. Oh, sorry, second years, right? Sorry, we are all in second year. Yeah, second years. So this is what we do. So this is very similar to this formula, right? If you see, so if you carefully observe, this is like expected value of x given y equal to 1 into probability y equal to 1 plus expected value of x given y equal to 2 into probability y equal to 2, okay, plus expected value of x given y equal to 3 into probability of y equal to 3, and then finally expected value of x given y equal to 4 into probability y equal to 4. So this is not really that surprising. I hope everybody understands it now very intuitively. Okay. So today we will continue on this, and we will talk about new things around this. All right. So that is the thing. So yesterday we saw a few applications of this formula. So we saw some applications of this iterated expectation formula. We saw a few applications of that. So let's continue and try to see a few more applications. So are there any questions so far? Okay, I see that there are a lot more students in the class today. So let me just tell something. So I understand that online classes are difficult, but there is a weightage that is assigned to your online participation that includes attendance in the class. Okay, so if there is some problem in the way I am teaching, and if there is some other issues due to which you cannot be present, for example, if you are keeping sick, or if you have some internet issues at your hometown, all of these things, you please let me know. Okay, but don't miss classes, because I don't have to manually take your attendance. The Google Meet will give me at the end of the class how many students attended and for what duration. Okay, so please don't miss classes. If there is some problem that you are having, let me know. Okay, if you're not following what I'm teaching, again you can let me know, and I will try to change as you like. Okay, so all these things can be arranged, but you have to let us know. All right. So coming back, so this is the important formula that we understood just a few slides back. And now let us try to look at an application. So we will use this to compute basically now. So using this formula, we will try to compute mean of geometric random variable. So this is again, you have done this. Okay, so so the question you may be wondering, why are we talking about this again? But here in this discussion that I'm going to do, you will see that this discussion will use this iterated formula, and the whole discussion becomes very simple. All right. So let's say n is a geometric random variable with the parameter p. So just to refresh your memory. So what this means is there is a sequence of coin tosses. Okay, so something like, let's say, tail, 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 and then head, tail, and so on. Okay. So what the geometric random variable n is capturing is the number of tosses required before you observe the first head. Okay, so this is the geometric random variable. We have seen this even in the Bernoulli process. Okay, so this is n. So what we are going to use is we are going to try to find the expected value of n. Okay, so that is the objective. And now we have to basically use this iterated formula. Okay, and we have to compute using this iterated formula. Okay, so now for that I have to define what is y. Okay, so now y I will define in a very peculiar way. So this is going to be like a Bernoulli random variable. Okay, it is a Bernoulli random variable for the first coin toss. So it is 1 if first coin toss is head. Okay, 0 otherwise. All right. So it's a very simple random variable. It is just the first coin toss, and if it is 1, if the first coin toss is head, 0 otherwise. Okay, so using this y, I will try to compute the expected value of n. All right. So yeah, so what is the number of tosses required to get the first head if y is equal to 1? So given that the first coin toss is head, what is the probability that, what is the expected value that you will get the first head, the geometric random variable? What is this going to be? Yes?
1. 1.
Yeah, correct. That's correct. So does everybody in the class also understand this? Can I just quickly have a quick poll to see if things are okay so far? Okay, so Siddhant, I will repeat. Rest seem to be okay. So, all right. So what we are talking about is a number of coin tosses that I need to do till I see the first head. All right. So that is n, and I want to find out the expected value of n. Okay. So I would like to use the iterated formula that we learned yesterday. Okay, and for that I need to define another random variable so that I can condition on that. So the another random variable that I'm going to choose for this is the outcome of the first coin toss. So the first coin toss can be a head or a tail. If it is a head, the random variable that I've chosen y will be 1. All right. So basically I'm conditioning on the event of the outcome of the first coin toss. So now if I say that the first coin toss is head, and I ask you, given that I have told you that the first coin toss is head, and then I'm asking you how many times do you have to toss till you get a head, what would you say? It has to be 1 itself, right? Because the first coin toss itself gave you a head. Okay. I hope this is clear to you, Siddhant. All right. So that is it. So this is absolutely simple. I can understand you might have got confused because it's so simple. But in any case, so this is this. Then what about py equal to 1? So this is easy, right? So this is what's the chance of getting the first coin toss as head? This is equal to p. Okay, so yes, someone has any questions? All right. Okay, so now coming to the difficult part. So what is the expected value of n given y is equal to 0. Okay, so this will require some explanation, but let's do that. Okay, so I'm telling you, so you have a sequence of coin tosses. The first one turns out to be a tail. Okay, so this is a first one turns out to be a tail. I don't know how this is going to behave. Okay, I don't know how long I have to wait to see this. Okay, now thing is, first one is a tail. That's all I know because I'm conditioned for this. So now when I start observing from here, okay, I start observing from here. We know that geometric random variable is memoryless, right? So if you look at the rest of the lifetime, this however long it takes, okay, this before you see the first head, that will continue to be the same distribution as geometric. So we know the distribution of remaining, or remaining is one choice of word, or coin tosses. Okay, distribution of coin tosses henceforth, okay, will also be geometric, right? Because see, this is like your IPL, right? So assume that you have a fair coin. Okay, in the first match of the IPL, some outcome came. Let's say it was a tail. Okay, and you are interested to see when the coin gives you a head. Okay, just because the first coin toss was a tail, it doesn't mean that anything new is going to happen. It is every time you do a coin toss, it's an independent coin toss. So this itself is a memoryless thing. So here, the number of rounds before you see the next head, you will expect that to be E of n itself. Okay, so this is going to be E of n. But you know, the first coin toss was already a tail. So there will be a 1 coming in here. Okay, so this is going to be 1 plus E of n. Okay, so this is like a recursive equation that we will have. Okay, and let me just finish the discussion by just writing this probability. This is easy. This is 1 minus p. Okay, so let me just wait for any questions from the class. Is there any questions? Are things clear? Can I again have a quick poll at this point? Okay. So if there is someone who wants me to repeat again, I would be happy to do. But if things are clear, then we will move on. Okay, so let's move on. So now we have all the elements that we need to compute E of n. So what is that going to be? E of n is going to be p y equal to 1 into expected value of n given y equal to 1 plus p y equal to 0 into expected value that n given y equal to 0. Okay, let me choose slightly a different color for contrast. So what do we have? E of n. So this is going to be p times 1, right? P times 1, p into 1 plus 1 minus p times 1 plus E of n. Okay, yes, so that's good. So let's do some simplification. So if you simplify, this will be this 1 minus p will be here, 1 minus p plus p will be 1. So the right hand side will be 1. And then here it will be 1 minus p times E of n. When I take it to the other side, this 1 E of n and then 1 E of n cancels. So I will be left with p times E of n. Okay, so now upon simplification, we can see E of n is going to be 1 over p. Okay. So I hope this example conveys to you that this iterated expectation has a very useful way. Sometimes you will be able to compute these expectations quite easily if you are if you just observe some of the things here. All right. So this is one example that I wanted to talk about. This is, by the way, in Sheldon Ross. This is example 3.11. So moving on, there is another example. Why am I running through the examples? Why didn't I give you to read it on your own? I just feel like you need some kind of a push to understand this, because this is kind of can be very confusing because of the notation. All right. So that's why I'm spending more time than what Sitsiklis does. I'm hoping that this is useful. This is useful in the sense that it is used very often in machine learning. This conditional expectation is what you use for various kind of learning theories. All right. So it's good to know the theory, because that will allow you to tweak the algorithm. Only once you know the theory well, you can tweak the algorithm. All right. So that is why we are spending more time on this. So there is another interesting problem that I would like to do. This is example 3.15. So let's move on to that. Okay, so what this is looking at is you are going to do a coin toss. Okay, till so there is, so basically what you have is independent coin tosses. Okay, this is sometimes called as trials, independent trials. Okay, and success probability is P. Okay, this is so far okay. Looks like it is a Bernoulli process, but you see now we will make a small change here. So these trials are performed. They are, you keep on doing these coin tosses till, okay, you see. So basically you repeat till you see K consecutive successes. Consecutive successes. Okay, so this is not the same thing as K successes. Okay, so what is the difference between K consecutive successes and K successes? So let's say K equal to 3. Okay, so K equal to 3 successes, if you are only interested in that, so you can stop when you have something like this. Let's say tail, tail, head, tail, tail, head, tail, head. So now you have got 1, 2, and 3 success. Okay, but consecutive success means this is not yet done. Okay, because the three heads are not together. So consecutive success will be something like you go on. Okay, tail, head. Okay, then tail, tail. Okay, then you will go on till you see 3 heads consecutively, one after the other. Okay, so this is when you stop. Here, you stop. Okay, so this is basically this random variable that we are talking about. Okay, so I hope the difference is clear. Okay, so what we are interested in, so suppose let's say nk is the random variable, is the number of trials required for k consecutive successes. Okay, so what we are interested in is, as usual, we are interested to do what is the expected value of nk. Okay, so that's what we are interested in, and we have to condition on something, right? So what we are going to condition is something. Okay, so this is what we are interested to compute. So this will be expected value of nk given some event here. Okay, so that is what we are that I'm going to be interested in, and this event we have to tell. Okay, so what we are going to condition is on this event. So let me condition this on a y. Okay, y is the event that Okay, so the y is the event that you have k minus 1 consecutive. So this is going to be 1 or 0. 1 if k minus 1. Okay, this is going to be a little more complicated than I thought it would be. So let's not go here just a little bit. Okay, so they don't. So this is going to be a little difficult. Let me just write it. So what they do is they divide the random variable nk into two things. Okay, so they say expect. So this nk can happen only if you have k minus 1 successes. Okay, and then so this random variable nk will be equal to the number of times till you get k minus 1 successes plus the number of rounds required to go from k minus 1 to k successes. Okay, so that is the thing. Okay, so I hope let's look at this equation. So basically what we are going to use is instead of this, we will not use this directly. We will use this inbuilt in the scheme, but we will change it slightly. So what we are going to say is the number of trials required for k consecutive successes, okay, is this random variable. So whenever you have k successes, right? So if you look at here, there are k successes, k equal to 3. It is necessary that you should have had 2 successes first. This should have happened, and then something should have happened. Okay, so that is what we are going to say. So the expected number of, so the random variable nk will be equal to the thing that you have got k minus 1 successes, and then how many more trials do you need to get from k minus 1 successes to k consecutive successes. Okay, so now two things can happen. So let's say you have, so let's say you have k minus 1 successes. Okay, so this is k minus 1 successes. There can be two things that can happen at this point. You can have one more success and then you are done. So this will be done. Or you have a failure here, and then you'll have to wait for a whole bunch of time till you get a success. So ak minus 1k represents this uncertainty. Either it can be this or it can be this. Okay, so that's what ak minus 1 represents. And now we will apply expectation. So this will be expected value of nk is equal to expected value of nk minus 1 plus expected value of ak minus 1 comma k. Okay, so now for simplification of the notation, I'm going to call, let us denote mk to be equal to expected value of nk. So that's what we will do. So what this gives us is a equation like this: mk is equal to mk minus 1 plus expected value of ak minus 1 comma k. Okay, so now for this ak minus 1, this event, now we will condition on whether you get a head or tail. So this will be, so let's look at this event. So let me write it here with a different color. Expected value of ak minus 1 comma k, we will condition on. Now here is where we will use the iterated formula. ak minus 1 comma k given y. Okay, and y will be 1 if you get a head here, 0 if you get a tail. Okay, so let's try to analyze this. Okay, so this is the easy part. So what is this here, guys? So let us say ak minus 1 comma k is the number of rounds required till you get k consecutive successes, given that you have already got k minus 1 successes. So given that y is equal to 1, what is the expected value here? Can someone tell me?
1.
Okay. So this is the easy part. So let me just pause and ask if people follow this. So till here, is it okay? Do you want me to explain some things? Can I have a quick poll?
Sir, can you please explain what is Y?
Okay, so let me just, since there was some kind of a glitch, let me just begin once again and tell this problem once again. So the idea is that there are independent coin tosses, and each coin toss gives a head with a probability P. This is very similar to what you have seen in Bernoulli. Okay, so that consecutive Bernoulli process, that's exactly what it is. But what you are going to do is, in this particular experiment, you will do tosses till you see k successes one after the other. All right. So in this figure, the blue represents, this part of the figure represents what is the meaning of having just k successes. Okay, not consecutive, just k successes. So here you see there are already 3 successes and you can stop. But k consecutive successes is not achieved till here. So you continue to do coin toss till you get exactly k successes one after the other. So this is what we are interested to find. We are interested to find expected value of nk for this k successes. All right. So now, since this problem, when I was approaching, I realized that the text does not condition for computing expected value of nk. It does not use this directly. Okay, it does something else. So what it actually does is it looks at the random variable nk. Okay, so whenever you have k consecutive successes, it must be the case that you would have had k minus 1 successes. Okay, so the first time that you reach nk successes, you must have had k minus 1 successes at some point. Okay, and that is what is nk minus 1. And after that, 2 things can happen. After that, either you have head, that means it becomes k successes, or you have a tail, and then again you have a sequence of whole things happening here. Okay, so that is what this random variable represents. Now, when you take expectation due to linearity, you have this result. Okay, and now in order to compute this expected value of ak minus 1 comma k, what this means is that you are going to, what is the meaning of ak minus 1 comma k? This is the number of rounds required in expectation. It's a random thing, right? So it's not deterministic. So it's like, how many rounds do you need to have gone from k minus 1 consecutive successes to k successes? Okay, so there are 2 things that can happen. So that is the y. So if y equal to 1, that means after k minus 1 successes, you get a head, that is y equal to 1. And y equal to 0 is the case that after k minus 1 success, you get a tail. And then again, you are in a whole lot of trouble, because again, you will have to do coin tosses and wait till you get one more success. Okay, so that is what is this. So y equal to 1, k minus 1 successes are there, and I'm telling you y equal to 1, which means the next one is also a success. So how many rounds does it take from going from k minus 1 to k after this? So just one more round is enough. Okay, so that is what I was saying, and that's what y is. So Ramnath, does it answer your question?
Yes, sir.
Okay, so this is 1. Now, yeah, we also know what's the probability that y equal to 1. So this is going to be p. All right. So now let's do the other thing. So what's the expected value of ak minus 1 comma k given y equal to 0? Okay. So this is slightly more difficult, but you can understand that once you come over here, right? Okay, so once you come over here, this is as though you are starting at the first itself. Okay, so, but there is unfortunately, it's not as though, because you are telling that the next one is also a tail. Okay, so this is as though you have started from before, but it's like you have already got one verse. So this is going to be a 1 for this tail plus expected value of nk. You'll have to wait again because it's going to reset. The system has started again. So this is nothing but 1 plus nk. So is this clear to people? This second part, I understand that this can be confusing, but is it clear? Can I have a quick check? I don't see that many yeses. So if there is anything that I can help please let me know. Don't be shy. All right. So then now we are ready to write the complete recurrence relation. Okay, so let's do that. So mk is equal to mk minus 1 plus, here I'm going to write using the conditional formula. Okay, so let's do that. Let me first compute this here. Expected value, okay, let me not clutter the place by writing this, but so what we are going to do is I will write here and then, yeah, so let me just clear this. Yeah, so expected value of ak minus 1 comma k will be probability that y equal to 1 into expected value of ak minus 1 comma k given y equal to 1 plus probability that y equal to 0 into expected value of ak minus 1 comma k given y equal to 0. All right, so this is what it is. So this is p into 1, right? And then plus 1 minus p into this I told is 1 plus mk. So when we simplify this, this will become yeah, so this will become 1 plus 1 minus p times mk. So now we have a nice elegant recurrence relation. So applying this back up here, what you have is mk is equal to mk minus 1 plus 1 plus 1 minus p mk. Okay, so we have to bring all the mk's together. So when we do that, you'll have pmk, right? So that p I will take to the other side. It's 1 plus p plus mk minus 1 by p. Now what you do is, since this is true, so this is what the recurrence relation we got. So from this we can also understand that mk minus 1 is 1 over p plus mk minus 2 by p. So like that we keep doing till we get m0, m1. So m1 will be 1 over p plus m0 by p, right? M0 is considered to be 0. Okay, number of times, what is the number of rounds that you have to wait till you get 0 heads? 0. Okay, so basically m1 equal to 1 over p. Okay, so then m2 will be equal to 1 over p plus m1 by p. Okay, so this will be 1 over p plus 1 over p square. Okay, so like that, next you will have 1 over p plus 1 over p square plus 1 over p cube. So that's why mk will be equal to 1 over p plus 1 over p squared plus 1 over p power k. Okay, so I will actually probably I will think about this. If there is, I don't want to overload you also, but I will try to make you do an experiment just to see that this is going to be true. I will just make a note of it, but let me see. I don't want to overload as I told. So yeah. Okay, so is this discussion clear? Let me know if you have any questions. So moving on. Okay, so the next part is on variances. So we are going to go from here to variances. So if there are no questions, let's do that. All right. So this is now I'm talking about section 3.4.1. Okay, so the first thing that we will do is we will recollect what is the formula of variance. Okay, so variance of x is expected value of x squared minus expected value of x, the whole thing square. This is a number, so we are squaring this. So this is the expected formula of variance. Now let's start directly by looking at a problem. Okay, so we will again look at geometric random variable. So we will look at geometric random variable with P as the probability of success, and let's say N is the geometric random variable with probability of success P. Okay, so we are interested in variance of N. Okay, so what is variance of N? It is going to be expected value of N square minus expected value of N, the whole thing square. We already know what is expected value of N. We have already done that. This is 1 over T. Okay, so we will use the idea that we have learned to compute expected value of N square. Okay, so expected value of N square, we will use the same idea. It's going to be expectation of expected value of N square given Y. Okay, so same iterated expectation. Instead of X, I'm taking some function of X, which is N square. Okay, so this is very same thing as before. Here again, we will have Y equal to 1 or 0 as before. Okay, so it will be 1 if first trial is head. Okay, 0 otherwise. So same idea. So we will use the same thing. So what is expected value of N square given Y equal to 1? So this also is easy. So let me ask the class. So what is this going to be? 1. So what is N? N is the number of trials I need to do till I get the first head. Okay, and I'm saying that the first coin toss itself is a head. Okay, so the number of trials required when Y equal to 1 is 1. Squaring that is also 1. Okay, so this is this. So this is the first thing. Now let's try to answer expected value of N square given Y equal to 0. Okay, so as before, so what we said was the first coin toss is a tail. So you have, I'm telling you Y equal to 0. So in this universe, okay, the first coin toss came as a tail. Okay, but how many rounds do you need to wait till I see the next head? That is continue to be the same random variable N, right? Correct, because I told you that this is a memoryless system. So if I start observing from this point onwards, the number of rounds that I need to wait till I see another head, the first head in this case, because the first one was a tail, the number of rounds that I need to wait till I see the first head is going to be N. So that is why it is going to be 1 plus N whole squared. So this is going to be expected value of 1 plus N whole squared. Yeah. Is this clear? Ramnath, is it clear?
Yes, sir. Sir, will it be like 1 plus expected value of N square?
No. So the thing is, I'm interested in expected value of N square. Okay. So N, the number of rounds that I need to wait, okay, given that I have seen Y equal to 0, okay, will be N from here onwards. Okay. So 1 plus N whole square, because I'm interested in N square. If you put expected value of N, then this is going to be a constant. So if I go with what you say, if I do this,
yeah, I got it, sir.
Yeah, it will be a constant, but that's not what it is, right? It's going to be a random variable. Siddhant, do you follow?
To some extent, sir. I'll just once look at again on YouTube once again when you push it again, then I'll get a bit hold of it.
Yeah. So let me just repeat, since people seem to be a little uncertain. So what I'm saying is there are two things that can happen, right? In the first coin toss, either you get a head or a tail. Let's say we got a tail, that means Y equal to 0. All right. And now in this universe that I'm having a tail, in this universe, the first one is a tail. I have to only restrict at that universe. Okay. And then I'm interested in how many more, like totally how many rounds does it take, I'm interested in. That is going to be 1 plus N, right? Correct, because 1 already has been wasted because I got a tail. So it is going to be 1 plus N rounds that I need to wait till I see the first head. Okay, why 1 is coming? Because the first one is a tail. I'm looking at the universe where Y is equal to 0. So that is why the total number of rounds that I have to wait will be 1 plus N. So since I'm interested in the expected value of the square, it is going to be expected value of 1 plus n whole square. Okay, so that is what it is. So yeah. So how are you following this discussion so far? Can I have a poll from others? Okay, good. Why is it not n minus 1? So Harshit is asking, why is it not n minus 1? All right. So Harshit, what happens is that if you remember, right? So when you put your when you look at the memorylessness property, what it says is that any day, so you have a sequences of heads and tails, right? So these are all the experiments that you are doing. Okay, so any day when you come in, okay, and if you start observing from this time onwards, okay, if you observe from this time onwards, so the number of rounds that you need to wait to see a head, this entire thing will be geometric, right? That is what the memoryless property says. Okay, so the number of rounds that you need to wait till you see the first head, okay, does not depend on when you start observing. If you don't observe anything till this point, but you start on this day, you see a tail. Then next day also you will see a tail. But the total number of rounds that you need to wait depends upon, depends on this duration. It doesn't depend on how many rounds have passed. Okay, so whatever has happened here has happened. Okay, henceforth it looks like geometric. Okay, so in the case that I'm conditioning on y equal to 0, that universe, the first one is a tail. Okay, but after that, whatever comes is going to be geometric. Okay, and that random variable is n. So that's why it is 1 plus n whole squared and not n minus 1, n minus 1. Harshit, I hope I have answered your question. Okay, so that is about it. So now we can start evaluating our expression. E of n squared is going to be 1 into p y equal to 1 plus, so this one we will simplify. This will be 1 plus n squared plus 2n. Okay, that is what this is. Okay, into p y equal to 0. Okay, so let's simplify further. This will be 1 plus 1. So e of 1 is 1. Then you have e of n squared plus 2 times e of n, which is 2 by p, into 1 minus p. Okay. So
sir, the first term should be e, right?
e of 1 is 1.
No. The first term in the second line, you have written 1 plus. It should be p plus, right? 1 into p of y equal to 1.
Oh yeah. Correct. Yeah. Thank you. Yes. Okay, so I will. So okay, we will write. Since I made a mistake, let me write more steps here. So what that will give us? So p into 1 minus p. So p plus 1 minus p. Okay. Let me do this myself. Why am I being lazy? So 1 minus p into e of n square plus 2 into 1 minus p by p. Okay, so that's what we have got so far. So this p and this p cancels. So I will have, and then this 1 minus p n squared and this e of n squared, the 1 cancels. So I'm left with p e of n squared, and then I'm left with 1 plus 2 into 1 minus p by p. So what that does is e of n square will give me 1 over p plus 2 into 1 minus p by p squared. Okay, and now we know that variance of n is e of n squared minus e of n whole squared. So this will be 1 over t plus 2 into 1 minus p by p squared minus e of n whole squared is 1 over p squared. Okay, so I don't know whether I have done all of this correctly, but I should have done it correctly anyway. So what that gives us is, yeah, so finally, I don't know if this is correct. If everything is all right, this gives us 1 minus p by p squared. Okay, I'm not doing the rest of it because we have to start the quiz. But yeah, so essentially this is what it is. So so I hope this is a good point to stop. So I won't do any recap because what we have been doing is essentially the same thing that we discussed yesterday. So there is one more topic that I need to cover. Maybe I will do that next week. Okay. And yeah, so for your next week quiz, I will give you specific things that you need to focus on. I will give you small readings. I won't make you read very difficult things, but small things. Okay. And mostly again, it will be based on what I taught in the class for the next week quiz. Okay, it will be simple. So yeah, so that's about it. So let me just stop here. And Varun, are you there?